Hi guys, welcome to part 2 of the video on section 11.9 on electron arrangements. Again, you can click on this link if you'd like maybe another perspective and a little more detail on what we're talking about in this series of videos. In the first video, we took a look at a couple of diagrams that tell us the order in which these electron orbitals will fill up with electrons. And then we related that to the periodic table. And what I'd like to do in this second video is just show you some of the rules that we use for filling electron orbitals and then give you a few examples. The first rule you already are familiar with. It's the idea that because of this property that we call electron spin, any box in the periodic table can only hold 2 electrons, and each of those electrons have to spin in opposite directions. If you like, you could call that stability. When these electrons are spinning opposite of one another, they're far more stable than if they were to be spinning in the same direction. Another way to think of that is if these arrows were spinning in the same direction, that's very much like a pencil standing on its tip. It's not going to stay that way. It's not stable. When the arrows, or when the electrons are spinning in opposite directions, that's like a pencil that's fallen over on the table. It's much more stable than if it's on its tip. And so in the same way that you could say the pencil wants to be fallen over on the table, as opposed to wanting to be standing on its tip, you could say that these electrons want to spin opposite of each other. They do not want to spin in the same direction. You don't have to use this M notation, the plus and the minus half notation. You can ignore that for the purposes of this class. I'm also not going to ask you, I don't believe I ask you to give a name to this next idea. It's called Hund's rule, but I don't think I ask you this on any quizzes or homework questions. But the idea is that you've got to put 1 electron in each available sublevel. And only after you've stuck 1 electron into each available sublevel can you go back and start putting a second electron, spinning in the opposite direction, into each box. Again, the idea here is that all the electrons are negatively charged, which means there's going to be a very robust, strong electrical force repelling them all from each other. They want to be as far away from each other as they can get. What that means is they're going to go into this box, and then this box, and then this box. They're much more stable by themselves than they are with a second electron. So you can think about this whole thing in terms of stability. From an electron's point of view, the best situation is to have the box all to itself. The second best, or most stable situation, is to share a box with 1 other electron spinning in the opposite direction. And the worst possibility would be to share the box with another electron, having them both spin in the same direction. So this is how you'll fill up boxes for the p orbital, but this would also apply to d orbitals, which will have 5 boxes, and f orbitals with 7 boxes. Little bit of language here. Anytime you've got an electron all by itself in the box, again, the best case scenario, that's an unpaired electron. Broadly speaking, unpaired electrons are the most stable. Here would be another example. Here would be more examples down here. Anytime you have 2 electrons in the same orbital, in the same sublevel, spinning in opposite directions, those are called paired electrons. You'll notice that there's some reference to being paramagnetic here. We're not going to get into the magnetism or the magnetic consequences of paired versus unpaired electrons. If that's interesting to you, there is, I should have linked it here, but there's a video by Minute Physics on YouTube. So if you type in Minute Physics magnetism, you can watch that video, and they go into a bit of detail on how these electron spins for paired electrons versus electron spins for unpaired electrons lead to magnets, right? Magnetic properties of materials. So how do we fill up these orbitals? Well, what I'm going to do is start with hydrogen, and then we'll go through the first several elements. Hydrogen only has 1 electron. So according to this picture, hydrogen's 1 electron is going to occupy, the lowest available energy state. So we start with all of these energy states open. Again, the orbitals are always there. An orbital is just a region of space. So the space around a nucleus is always there. It's just that until you put electrons into that space, it's empty. And so the first electron is going to come down and it's going to occupy this 1s orbital. And so we write 1s, 1 being the size, s being the shape, and the superscript means we have 1 electron in that orbital. Sometimes people say, Cato, does it matter if I put the electrons spinning up or spinning down? And the answer is, if there's only one of them, no, it doesn't really matter. Now, having said that, you'll notice over here it says if you have one spinning up and one spinning down, that's incorrect. Technically, if you should have them spinning in the same direction, even if they're in separate boxes. But you could have them both pointing down. Or you can have them both pointing up. You just have to pick a direction, and as long as you have unpaired electrons, make them all point in the same direction. And so we have this 1 electron spinning up. Now we go to helium. Helium has 2 electrons. They occupy the lowest available state, so 1s, and now the superscript changes to 2 because we have 2 electrons, and you do have to have these 2 electrons point in opposite directions. Now we go to lithium. Lithium has 3 electrons. The first 2 are going to occupy the 1s orbital, but now it's full. So we move on to the next lowest available energy state, which is 2s. Or if you like this diagram, once we've filled 1s, we loop back and we fill 2s. Or if you like this diagram, once we've filled 1s, we have to move on to 2s. 2 of lithium's 3 electrons fit into the 1s orbital. The third electron has to go into this 2s orbital, spinning up. It's an unpaired electron. Next, we move on to beryllium. Beryllium has 4 electrons. The first 2 go into the 1s orbital, spinning in opposite directions. The next 2 go into the 2s orbital, and now we've filled those. The 1s orbital is now full. The 2s orbital is now full. And so, when we move on to boron and larger elements, we'll have to start filling up the 2p orbital. Again, we filled up 1s, we loop back, we filled up 2s, we've looped back, we filled up 2p. Or if you like this picture, we filled up 1s, we filled up 2s, follow the arrows, we're going to start working on 2p, or start filling 2p. And you can see that's exactly what happens here. Since the p orbital holds 6 electrons, the next 6 elements, boron through neon, are just filling up this 2p orbital. You'll notice here's a question people ask. They say, Cato, do I have to put this electron into the box on the left side? Could I put it into the middle or even the right side if I wanted? The answer is yeah, you can. The electron doesn't care. Remember, these boxes represent directions in space. So the left box represents this, the middle box represents this, the right box represents this. The electron doesn't really care, it just has to occupy one of these all by itself. But usually chemists start on the left side. So if you want to break out, you fill in one box. If you want to conform to what chemists traditionally do, fill up the left box and then the middle box and then the right box. You absolutely cannot try to stick any of these electrons in the 2p orbital into the same box until each box has 1 electron. Now, with the next electron, we can start dropping in and filling up the boxes, making paired electrons. Finally, at neon, we have 10 electrons. We've filled up the 1s, we've filled up the 2s, we've filled up the 2p, and we're finished, right? Another thing you'll notice here is that we just keep adding electrons here. So it's always 1s2, 2s2, 2p1, 1s2, 2s2, 2p2, 1s2, 2s2, 2p3, and so on and so forth. This notation is simply counting how many electrons there are in the 2p orbital, right? 1, 2, 3, 4. This notation tells us nothing about which box the electrons are in or whether they're paired or unpaired or anything like that. Final comment here, I guess, final thing I can think of to say about this is that these orbital diagram, and that's what they're called. These boxes are called orbital diagrams. This 1s2, 2s2, 2p4, this notation on the left side is called an electron abbreviation. You should be able to do both of them. Although in May of 2020 we're on quarantine, and so this is probably what I'll have you writing as opposed to drawing a lot of boxes. But if we're meeting in class, God willing, you'll be drawing these boxes too. This shows us the valence electrons. Remember, the valence electrons are on the outside of the atom. Well, the 2's, remember these numbers represent size. So the 2's are larger. That means they're on the outside. The 1 is smaller, so it's on the inside. These represent core electrons, but the 2s and the 2p represent valence electrons. And sure enough, beryllium has 3 valence electrons. Carbon, has 4 valence electrons. Nitrogen has 5 valence electrons, oxygen has 6 valence electrons, and so on and so forth until you get to neon, which is completely stable because it doesn't need any more electrons. It's got its 8. Another thing you'll notice is that oxygen, for example, will almost always have an ionic charge of 2- because it has 2 spaces right here that it wants to fill up with electrons. Adding an electron into this box of the 2p orbital and adding a second electron into this box of the 2p orbital gives oxygen 2 extra electrons, and that's where its 2- charge would come from. Or fluorine, being a halogen, will form a negative charge because all it wants is 1 more electron in its 2p orbital to be stable. When it gets that electron, it gets a negative ionic charge.